In this video, we're going to look at how to detect changes in particle data. In this case, we've got some particles being created on the surface, and then they follow that surface. And what we want to know is particles who are moving fast enough. We want to go ahead and detect some threshold, and if they're moving fast enough, then have them do something else. One of the problems here is that particles who follow a surface like this actually do not receive any velocity information. We'll go ahead and just confirm that here. So we've got our particles. Let's get that, get a memory, and detect what is my velocity value. Let's turn on debug, and so you can see all the values coming out of here are all zeros, even though we can see that the particles are in fact moving to stay stuck on that surface. This problem happens a lot whenever you're going to rely on some other animated surface and using some kind of surface follow or surface position. So if you need some kind of threshold that says, hey, my particle's moving too much, it's got some inferred speed, we're going to need to be able to detect how much speed or position change is being affecting that particle, and then do something based on that. So really simply, the way we're going to do this is we're going to store particle's position at a certain time and then check it at another time and calculate that distance, and if the distance is large enough, then we're going to go ahead and say, hey, particle, go do something else. So we're just going to reuse this rule here. We'll call this store data, and we're going to tell the particles, actually we don't want velocity in this case, and this variable can go away. We're just going to use position for now, and the depth is going to be important because we're going to need to compare it to a certain time ago, and so we're going to need some kind of depth history. There are ways you can set this up so that you don't have to, but it's easier if you do. So, and it's also not as limiting. We're going to go ahead and just say depth 99, which, remember, depth is 0 base, so this is 100 cells in which we can store position data, so a history of 100 values. If we wanted to be really efficient, we could set this to 1 and use some kind of counter variable or counter setup that would only store the position at certain points in time. Maybe we'll take a look at that. For now, we'll go ahead and say depth of 99. Usually you don't see too much overhead as far as cache sizes when you use a lot of variables like this. So we'll go ahead and drop in our position input, and so we're just going to use a particle and connect that into this position input. And because of in TP4 we've got a position type input type, it's able to automatically derive that from the particles, so you don't have to feed it specifically a position like you did in TP3. Okay, so here we've got every time sample, which right now we're set to per frame. Every time sample, all particles in the all group are going to go ahead and store their positions. And what we're going to do then is we're going to go ahead and in the next rule, let's get these organized here. Let's get edit on the fly. Oh, plus we were way out there in time. So, and let's do this. Let's say compare data. So in compare data, of course, we want to compare our current position with our position from memory, at whatever depth, maybe 1 or 2 or 10 or however far back in time you want to look, however much change in time you want to compare against. So let's get our all particles, our memory, access, position as an output. We know we're going to need a distance check because we want to compare that position with my current position. And actually, of course, remember, because of the way TP evaluates the tree, it's top down, so all in one time sample, it's going to step through all these rules and evaluate whatever it can. So if we're going to store my current position here, we certainly don't want to compare against my current position here. That distance will always be 0, so we have to specify a depth at this point. Use integer, set it to 1, so we're just looking one time sample ago, and remember our time samples right now are per frame. And then we'll go ahead and use a memory to expose this distance value. Just put this in here as distance change. And it does not need a depth. We're only going to check this once, really. So let's get that clarified there. and get our distance piped in here. Turn on debug, and let's take a look at what kind of distances we're getting. Actually, let's make it easier on ourselves. Let's go ahead and just birth one particle for now. Okay, so our particle, you see we've got this wave mesh here, a plane with some noise and a soft selection, so only part of it's really getting the displacement. And what we'll see there, and I don't think my video card will actually put that particle out there, too bad. But what we'll see is as we scrub forward, the distance difference per time sample here is pretty low for this particle. There we go, we get into the 0.4s. So a change in 0.4 world units, 0.5, 0.9. So what we'll do is we'll actually set up a situation where we'll add another Boolean value here. We'll call it moved too far, and its depth can be 0 also. And what we'll do is we'll have, let's get this, move too far, we want to be an input, and so when this distance reaches or exceeds a threshold, so we'll set our distance, our threshold, 0.9. Then go ahead and turn on this memory here. We don't need that. Well, we can leave the distance change, I guess. But we'll go ahead and use it to set this move too far variable. We'll set that to true. And then what we're going to do, we're going to need another rule, actually, where we actually do something with that, I've moved too far variable. We'll call it moved too far. And let's grab our variable. Move too far. Yes, I have moved too far. So if I've moved too far, actually velocity is not going to make much sense because our particles are being told to follow the surface. Let's tell them not to follow the surface. And actually we don't need that rule then. What we'll do is we'll say, hey, I've moved too far, so I set my variable to true. And what we'll do is we'll ask our surface here, we'll say, hey, if I have not moved too far, then keep me following the surface. So we'll use an on in here to control when this happens. So we'll say, hey, we want to know what the value of this move too far is. If it's false, then I want this to be true. So false to true, we're going to need an invert. It's just going to invert whatever value. If it's false coming in, it outputs true. If it's true coming in, it outputs false. So let's go ahead and just take a look. And wouldn't you know it, nothing happens. And part of the reason for that is because at birth, this particle does not have a true value in here or a false value. And so this position, surface position, never gets updated. What we have to do is we have to say, at birth, initialize this particle to say, hey, I have not moved too far. And so this, now being false, is going to allow the surface come out false, comes out true, and so then it's going to start recording the position, and then if that position is beyond that threshold, then it will say, hey, you know what, I've moved too far. Yes, I have. Okay, so there's our particle, and boom, then he just kind of stops moving in there. Now that is a little bit boring. Let's actually throw some velocity in there. So in this case, we know this is going to be true at some point, and so we're going to use that to control when this velocity happens. And let's send them up like that. Now we don't really need debug at this point. And there he goes. Okay, so on a mass scale, what do we have when we have, let's get 100 particles out here. And we'll see that when that change, when they change enough, then they get thrown up pretty quick. So eventually all those guys who are over here on the animated noise portion are going to reach that threshold, whereas all these guys, their distance never changes, frame over frame, so they do not become released. Okay, so that is detecting position difference over time. And of course, if you want to increase the amount of distance, you can start increasing how far back in time you look. So if I want to look 2 frames ago, then these things are going to come off sooner. Let's actually check that. So with a depth of 1, our first guy comes off around 50, 58, 59. So let's go ahead and make that, say, 2, or let's go extreme, let's say 4. So if you set it to 4, yeah, even at 35, you start to get a whole bunch of particles breaking off. That all makes sense, of course. You're looking further back in time, so they have displaced themselves further in time. Okay, so that's all pretty basic. Let's go ahead and save this out, and we will move on. We'll save this file. This is detecting changes in particle data.